Today we're going to talk about Planck's postulate. According to Planck, electrons can only absorb or emit discrete values of energy, h nu. So we know that according to him, E is equal to the Planck's constant h multiplied by its frequency. Now, what we're saying here, or what he's saying here, is that let's say I have an electron in its ground state, and I want this electron to move to the next energy level in E2 so that it becomes in an excited state. Okay? Now, what he's saying is that for this to happen, the energy input, which can be in the form of heat, light, or electricity, must be absorbed by the electron in exactly the amount what we call delta E. Delta E is equal to the difference between the energies of the final energy level and the initial energy level. And so this is the part where they absorb. We expect that the delta E value for this one is positive, okay? Because E2 is greater than E1. So if you provide an amount of energy that is less than this delta E, then the electron will not move. That is basically what he's telling us, that it can only absorb or emit discrete values of energy. And we also know that because the energy is neither created nor destroyed, the law of conservation of energy, when this electron falls back to its original energy level, the energy output, in this case, so the energy will be emitted. So that's emit. But the thing here is that it's only emitted in the form of electromagnetic radiation, which we call light. So the delta E in this case will be E1 minus E2. That is when it emits the energy. And the delta E value of this one could be negative. So when an electron moves up to a higher energy level, the delta E is positive. And when it moves up to a lower energy level, the delta E is negative. But the thing here is that every delta E value is associated with a certain frequency, as you can see from the equation, and every frequency is associated to a wavelength, which from our equation, we know that C is equal to lambda nu, and therefore E is equal to hc over lambda. So we notice here that frequency and energy are directly proportional, while energy and lambda or wavelength are actually inversely proportional. So if my energy is high, meaning I have a higher delta E, we expect the frequency to be high as well, and the wavelength to be short, and that's why it's going to be like this. On the other hand, if the energy is low, we expect the frequency to be low and the lambda to be long. And there you go. So for example, if there are several energy levels in your atom, so we have it here. So supposing I have here energy number 1, I have here energy number 2, and energy level number 3. And let's say an electron is making a transition. By the way, the delta E that we call here is actually what we call transition energy, before I forget. So if I have my electron here, and it moves from 3 to 2, how does this compare to an electron that moves from 3 going to 1? Oh, let's see. So remember that for the electron, the movement from 3 going to 2, your delta E is equal to final minus initial. We expect this to be a negative number. So, but remember that this one has a lower delta E. And because of that, we expect that transition, the green one, to have a lower frequency. At the same time, a longer wavelength. On the other hand, if we look at the red one, okay, it is a transition from 3 to 1. And you can see that it is a bigger transition. This is the transition for this, going from 3 to 1. And the green will be your delta E going from 3 to 2. So the red one, the 3 to 1 transition, delta E is equal to E1 minus E3. And because it has a higher delta E, you expect that it will release light at a higher frequency and shorter wavelength. There you go. That's our introduction to the Planck's postulate.